Okay, good. So welcome to the final problem solving session of the discrete mathematics course. Okay, and this week will be based on some of the advanced topics. Okay, some are based on counting and some are based on something called group theory, which is one of the slightly more advanced uh, areas in consideration of for this course. Okay, so we'll get there in a while. Okay, first I want to dabble a bit into the initial parts. Okay, first we'll look at graph colorings. Okay, so we'll look at what chromatic polynomials are. Okay, and we'll solve a few problems and partitions, and we'll solve a few problems there. But the main focus of this session will be on group theory. Okay, so as you may have seen in the lectures, firstly, what is a chromatic number? Chromatic number is the minimum number of colors needed to color a graph properly. Okay, what do I mean by proper coloring? A proper coloring means that no two vertices have the same color. Okay, no two adjacent vertices, which means which are vertices which are connected by an edge. Okay, for example, let's say I color this particular node red, and something like this is not allowed. Why? Because they are connected by an edge, so they are not allowed to have the same colors. Okay, so I need to choose a different color. Let's say blue. Okay, and then I can choose a red again here. Why? Because they are not connected by an edge, so I can choose the same color as this particular vertex. Next, what I do, I uh, I can choose a blue here, or I can choose, let's say, a green here. This is allowed. This is perfectly allowed. This is a proper coloring. Okay, but this is not the minimum one. Chromatic number would represent the minimum number of colors. Because I'm using three colors here, and if I use a blue color here, I'll just get two colors. So this is the chromatic number. Okay, chromatic number. Okay, or also represented by chi. Okay, of graph G is equal to 2 in this case. Okay, minimum number of colors needed to color this graph properly. Well, now the question comes, what is a chromatic polynomial? In the lectures you may have seen that given lambda many colors, okay, I give you some lambda colors, we are asking how many ways there are to color a graph properly. Okay, by proper I mean that, again, that no two adjacent colors should be the same. Okay, no two adjacent vertices should have the same color. So, well, a simple example would be, I am given this path. I have lambda many choices. I have lambda colors, okay, red, blue, green, and so on. I have lambda many choices to color this vertex. So let's say I chose one of the lambda colors. Okay, I chose one of the lambda colors. Let's say I chose red, and I cannot use red here again, but I am allowed to choose from the remaining colors. So I have lambda minus 1 many choices here. So from there, let's say I chose blue from the lambda minus 1 choices. So next what I can do is, I cannot use blue, but I can choose red again, which means I have lambda minus 1 for the blue color, okay, choices. So again, I have lambda minus 1 choices for the last vertex here. Why? Because I'm going to choose, let's say, blue. Okay, so in any setting, okay, in any given any path, so I can use this kind of logic to solve it. Of course, this kind of logic will not always be possible, okay, for some different graphs, but we'll see how to handle that. But we see that, okay, by the product rule, okay, first one has lambda many choices, the second has lambda minus 1 many choices, and third has lambda minus 1 and lambda minus 1, which is lambda times lambda minus 1 cube, which is called the chromatic polynomial represented by C of G. Okay. So given lambda colors, I will tell you how many ways there are to color this graph G. As simple as that. Okay. So look at this particular graph. Okay, we are given lambda colors again. Okay. The question is, what are the number of ways to color the following graph? Okay. Try to think of a strategy maybe, and it's a very similar logic that we saw just now. So I'm given lambda colors. Okay, I need to color this graph properly. So how many ways are there to do it? Well, a similar logic follows. So say uh, consider vertex A. Okay, this particular vertex, and I am allowed to color with lambda many colors. I can choose any vertex actually for this simple kind of graph. Okay, you can choose any vertex, but let me choose A. Okay, I have lambda many choices. Okay, there are lambda choices to color A, and let's say I fix that color. Okay, let's say I chose a color. Say I color it with red. For the remaining vertices, okay, let's look at B now. Look at B. B cannot be colored with A's color, but it can be colored with all the remaining colors, which means there are lambda minus 1 choices. So there are lambda choices for A, there are lambda minus 1 choices for B. Now, just similarly observe C. For C, I cannot choose A's color. I cannot choose red. Okay, but I can choose B color. Can but choose B's color. So out of the total lambda colors, I'm only restricted saying that I cannot choose B's color. That is one color. So I have lambda minus 1 choices again. So similarly for others, I have lambda minus 1 choices for D, and I have lambda minus 1 choices for C. So chromatic polynomial of the graph G, okay, is equal to lambda times, okay, by the product rule, lambda times lambda minus 1 times lambda minus 1 times lambda minus 1 for all the other vertices surrounding, okay, to the 4. So for such a graph, given lambda colors, I can always tell how many ways there are to color this particular graph. Okay. So I hope that was clear. Now we'll look at a helpful technique, okay, to find the chromatic polynomial. Let's say CG represents the chromatic polynomial of a graph G. Okay. Next, what? Let E be an edge in the graph G. Okay, edge of the graph G. Then we have this formula. Okay, it was there in the lectures. C of G with the edge removed minus chromatic polynomial of G with the edge contracted. So what is meant by edge contraction? So if G is the following, okay, let's say something like this, okay, and this is E, then G, okay, then G minus E. What will G minus E look like? G minus E will look like the following. Okay, and what does G contract E look like? Okay, and G contract E. Okay, imagine like you have the edge E, right? It is connected to two vertices side by side. Now what do? You bring them together and fuse them. Okay, or in the lecture I think it was called coalesce them. Okay, together to form a single vertex is equal to you fuse these two uh, vertices into a single vertex, and this is what you get. So now you understand, right? So if I have to find the chromatic polynomial of this particular graph, what I need to do is I find the chromatic polynomial of this graph and this graph, okay, and then subtract the second from the first by the theorem. And and how do you obtain the chromatic polynomial from this graph? Well, you can use the theorem again. You can remove edges and contract and so on, or you can, if the graph is simple enough, then you can use this technique. Okay, I'll give you an example of this. Question says, what is the chromatic polynomial of the following graph? Let me call it G. Okay. So E, okay, or rather, okay, and A B C, okay, okay, sorry, this is E A B C D. So what I want to do is, okay, I cannot directly apply the previous technique. Okay, previous technique meaning that, okay, let's say I color one vertex with lambda and the other would be lambda and so on and so on. When there are large cycles, like in the case of this, I cannot do this. Okay, so what I will need to do is the following. Okay, I'll look for an edge that I can remove. Okay, it could be any edge actually, but this looks like a nice edge to remove, because if I remove this edge, I'll get a cycle. Okay, maybe I'll get a much simpler and structured answer. So I'll do exactly that. I'll call this edge E is already used, so I'll call this E prime. Okay. So what I'll do is I'll remove it. I'll find two different graphs in which one of which I'll remove E prime, edge E prime, and the other in which I fused them. I have contracted the edge. Okay. So this is G minus E. Okay. Now what do I get here? This is what I get. I get a cycle. What is the cycle called? Well, it's called a C5. The other case I want to look at is when it contracts. Why? Because I want to use the theorem at the end. Okay. So what I get now is after contracting is a structure which looks like this after contracting, right? So where this is your E, this is your A, and this is your C, and this is your E prime, okay, or B, D, whatever you can call. This is what we get. Well, by the theorem, I know that if I find the chromatic polynomial of this and this, then I'm done. Why? Because I'm just going to subtract the second one from the first. That is what my theorem says. But how do I even find the chromatic polynomial for them? Well, the trick is that I use the theorem once again. Okay, but here I have one thing is that I can easily analyze in this case. Okay, so let's look at this particular graph. Okay, the middle vertex. Let's say I color it with lambda many colors. Okay, then what I have here is this particular one to the right. Okay, it needs to be colored with the remaining lambda minus 1 colors. Cannot be colored with lambda again. Here too, towards the left, I have this triangular cycle. So here I must color with the remaining lambda minus 1 colors, and this final edge vertex out here, okay, cannot be colored with the one A is colored with, cannot be colored with what lambda is colored with. It needs to be colored with the remaining lambda minus 2 colors. So here the C of, okay, I'll call this graph say G prime. G prime is equal to lambda times lambda minus 1 square times lambda minus 2. I hope it's clear so far. So I've got the chromatic polynomial for this particular graph. What remains is the chromatic polynomial for this graph. Need C of C5. As soon as I get it, I'll get my answer. Okay. And how do I do this? I actually split it up once again. Okay, I choose an edge. Let's say this particular edge, I'll call it E double prime. Okay. Now what I'll do is I'll find G is C5 minus E double prime and C5 contract E double prime. So let's see what it looks like. C5 minus E double prime looks like this. Yeah. And what does C prime contract E double 5 look like? We get this is what we get after contracting. Okay. Well, now how do you now the answer is, oh, okay, if I need to find the chromatic polynomial for C5, I need to find the chromatic polynomial for this one and then subtract. Okay. And how do I find the chromatic polynomial? Well, in the first one, it's a path. So we know that previously we've seen for a path, it's quite simple. Okay. We just pick a particular color, okay, for some vertex at the end, okay. And the one next to it cannot be colored with the same color as the first graph, but the one to the third can be colored with the one the one at the beginning. Let's say it is again colored with red. That is allowed. And as seen in the lectures, actually all the remaining will be lambda minus 1, lambda minus 1, and so the chromatic number of this particular graph is equal to lambda times lambda minus 1 whole to the 4. Okay. Now remains C5 with edge contracted E double prime. This is nothing but C4. Okay. Now again, what will we do? We cannot do it directly. We need to use this theorem again, once again. So how do you use the theorem again? Well, choose one edge here. Let's say this E triple prime, this particular edge. Okay. I'll color it with blue. Now I'll split it. Okay, so after splitting, what do I get? I get a path of length 3, and I get I get a triangle graph. Now observe, in both the cases we know how to find the chromatic polynomial. What is the chromatic polynomial here? Lambda many colors for the first one, lambda minus 1 for the remaining. Okay, so here it is C of, what is this? This is a path, right? Path on 3 vertices is nothing but lambda times lambda minus 1 whole cube. And here we have a triangle graph, and we know that, it's lambda times lambda minus 1 times lambda minus 2. Okay, so C of C3 is lambda times lambda minus 1 times lambda minus 2. So now we know how to find the chromatic polynomial for everything below. So we'll just backtrack now. So for this particular graph, what is the chromatic polynomial? Okay, so which means that chromatic polynomial for C4, okay, is equal to lambda times lambda minus 1 whole cube minus lambda minus 1 lambda minus 2. Okay. Next, what do you have? This bigger one, C5. So chromatic polynomial for C5 is equal to this lambda times lambda minus 1 to the 4 minus C of C4. I'm not writing the expansion because it will be very big. And then we just keep backtracking. Okay. And now we got this big one, big chunk. And towards the right, we know what this is. So C of G prime. Okay. C of G equals C of 5 minus C of G prime. And we know what C of G prime is. C of G prime is simply lambda times lambda minus 1 square times lambda minus 2. Is that it? Yeah, lambda minus 1 times lambda minus 2. And C of C5, we know if it'll just be plugging in these values. And this is your answer. Okay. I mean, this was a bit complicated. There were lots of steps in between, but the steps were very repetitive. I hope you saw that. Okay. And I'm just trying to show that this theorem is quite powerful. You can apply it in various scenarios. There is a more straightforward formula also which uses some combinatorics. Okay, but I'm trying to use what was done in the lectures here. Okay, so I hope that is clear. Please let me know if there are any problems. Okay. Okay, let's continue then. Okay, let's quickly look at partitions. Oh, okay, Divya, clear, right? Okay, good. Okay, so let's quickly look at partitions. Okay, what is partition? I mean, there is the set kind of partition, but we are looking at partition in terms of numbers. Okay, so a partition is a number of ways that we can split a number as a sum of other numbers. Okay, for example, here we have 3. 3 can be written as 3. 3 can be written as 1 plus 2. 3 can also be written as 1 plus 1 plus 1. See, by the way, we are not considering something like 3 equals 2 plus 1. This and this are identical for us. It does not, the ordering does not matter. Okay, and finally, what do you have? You have distinct partitions. Okay, distinct partitions meaning partitions. Okay, those partitions. Okay, with no duplicate numbers. Example, 3 equals 3, 3 equals 1 plus 2. Okay, a non-example is 3 equals 1 plus 1 plus 1. Why? Because 1 is repeating 3 times. So such kind of repetitions do not come under distinct partitions. Partitions. Okay. Next, odd partitions. Partitions with only odd numbers. Okay. So partitions with only odd numbers, meaning how many partitions here are there? This consists of only odd numbers, okay, on the right hand side, and this has only odd numbers on the right hand side. Example, 3 equals 3, 3 equals 1 plus 1 plus 1, but 3 equals 1 plus 2 is not an example because there is 2 there. Okay, and you might have seen this theorem that number of distinct partitions is exactly equal to number of odd partitions. Okay. So for example, here in the case of 3, number of distinct partitions are 2. and number of odd partitions are also 2, as we see. Okay. Yeah. So let's do the simple question. Okay. Right. How many partitions does 5 have in total? How many distinct partitions and how many odd partitions? So number of partitions 5 has in total. Okay. How many ways can you write 5 as a sum of numbers? And how many distinct partitions are there? C. Oh, that is quite quick. Yes, C should. Yeah, C should be the correct answer as well. Yeah, let's see. Oh, I'll give you some more time. Well, let's begin by listing out all the partitions of 5. Okay. So 5 can be written as 1. Okay, 5 can be written as 5. 5 can be written as 1 plus 4. 5 can be written as 2 plus 3. 5 can be written as 3 plus 2, but that's the same thing. 4 plus 1, but that's the same thing. Now we need to look at bigger partitions. 1 plus um, 1 plus 2 plus 2. Okay. 5 can be written as 1 plus. Okay, let's write 1 here first. 1 plus 1 plus 3. 1 plus 2 plus 3. Okay. And okay. So far 5 can be written as 1 plus 3 is again gone. Now what is remaining? 2, 3, 1 plus 1 plus 1 plus 1 plus 1. Okay. This is another partition. And I think we need one final partition. 5 equals 1 plus 1 plus 1 plus 2. And if you observe, you cannot create more partitions. This is all you can create. And how many are there? Because see, once if you look at this, if you start grouping them, you get all partitions of 2 are already done for us. With 2 in it are already done for us. If you group 3, then all partitions with 3 is already done for us. So, and total number is equal to 7. So C should be the correct answer. That's right. And let's check whether the odd partitions and distinct partitions are also true or not. How many odd partitions are there? This is odd, and this is odd. This is odd. 3 odd partitions. And let us look at distinct partitions. Well, this is distinct. This is distinct. This is distinct. Well, okay, this is not distinct. But I see 1 plus 2. Okay, this is not a proper partition, right? 2 plus 3 is going on again. So we need one more partition actually. Am I missing something? 1 plus. Okay, 1 plus 2 plus 1. Yeah, 1 plus 1 plus 2 is not done. Okay, plus 2 plus
1 plus 2 plus 2.
2. Right, 1 plus 2 plus. Yeah, correct. Good. 1 plus 2 plus 2 was not done. Okay. Yeah, so this is also not this also has duplicate, so it's not distinct partition. This is also not a distinct partition. Yeah, so 3 distinct partition. Or you can also use the fact that um, the number of odd partitions is equal to number of distinct partitions. Okay, yeah, good. So the answer is C. So yeah, let's continue. The question says, what is the number of distinct partitions of 42 in terms of a coefficient of a polynomial? So you might have seen it in the lectures, right? But even if you don't recall, it's fine. So happens that you can represent number of partitions or number of distinct partitions and so on in terms of a coefficient of a polynomial, which means that you can find a generating function for it, in other words. So, well, what we simply do is we look at this polynomial, okay, p of x equals 1 plus x times 1 plus x square times 1 plus x cube times 1 plus x to the 4 and so on until 1 plus x to the 42. And this is my polynomial, and then uh, number of distinct partitions, which is shown by PD, okay, of 42 is equal to the 42nd or rather coefficient of x to the 42 in my polynomial. And you may have seen the argument, but I'll just tell you quickly why this is so. Okay, then we'll quickly move down to the group theory section. Because each of these terms actually tell us whether we are selecting a number or not. This tells us to choose between 1 is present or not, 2 is present or not, and so on. And if it is present, then I'll take an x which will multiply with another term. Let's say I took a 2, then it will multiply with 1, which means I'm doing a 1 plus 2. The degrees will add up. And finally, if I look at the coefficient of 42, it means that the degree actually, after multiplicating several times, actually added up to a 42. So I'll get 1 plus 2 plus 0 plus 4, okay, if I choose this, and so on, is equal to 42. So this shows the number of distinct partitions. Why is it distinct? Because you see that I'm choosing a number only once. I cannot choose a 1 here and later again in some other term I choose a 1. No, that cannot happen. If I choose a 4 here, then in the following terms I don't have a 4 to choose from. So I cannot have something like 1 plus 4 plus 4 or something. So this is distinct. And this coefficient, okay, this coefficient of the x to the 42 will give me the number of partitions, number of distinct partitions of 42. Okay. Do let me know if you want me to repeat it. Else we'll just move on and solve the remaining questions. So, yeah, I hope it's fine. Okay. So, now we'll look at group theory, okay? Now, group theory is an immensely interesting field, okay? It belongs to a larger field of mathematics, which is called algebra, okay, or abstract algebra. It is the study of uh, operations, okay, but it's also the study of symmetry, and you also have something called computational group theory, which is a science of it's the field of computer science, which is dealing with finding better algorithms to solve problems in group theory. And it's also immensely used in what is called coding theory. Okay, coding theory is consists of error correcting codes, how you send information and get back information. It's used in automata theory in computer science. It's used all over the place. Okay, and in pure mathematics also it's a very important place, and it is one of the elemental gateways to the world of abstract algebra. Okay, and so what is a group? Let's begin by talking about groups. A group is a set, okay, S, okay, along with an operation. I'll call it star. It could be any other operation, okay, and a group should necessarily satisfy the following properties. Okay, so a group should have closure. What do you mean by closure? It means if I multiply elements of the group, okay, let's say A star B, okay, for all AB, A star B should be contained within the group itself. Why do I call it closed? It's as if it's a room and there's a door which is locked. So even if I multiply elements, okay, I multiply A and B together, it cannot happen that they are going outside the room. The room is closed in that sense. That is when you say the group is closed, the structure is closed. Okay, when you multiply two elements and they still remain within the same property. In this case, I multiply two elements and they belong to the same group. Okay, we'll soon see examples for these. Okay, and okay, I'll give you an example. Multiplying real numbers together. If I multiply two real numbers together, I always get another real number. So the set of real numbers, all real numbers is closed. Okay, they satisfy the closure property. Associativity. Associativity is of the following form: A star B star C, okay, is equal to A star B star C. Okay, and this shows that bracketing does not matter. We say the operation is associative. It does not matter whether I first multiply AB and then multiply with C, and it is equivalent to multiplying with BC first and then multiplying with A. Okay, identity means, okay, there exists a unique element E, okay, and such that A star, any element A, okay, for all A, such that A star E is equal to A. For example, in the case of integers or real numbers, the number 1 is the identity element. Anything multiplied with 1 will give itself. And finally, inverse. Inverse means that for all A, there exists an A inverse such that A times A inverse equals E. Example, 6 times 1 by 6 equals 1. This is your identity element. On multiplying with its inverse, okay, the operation should give me the identity element. Okay, good. So yeah, let's look at these examples. Okay, the question says which of the following are groups. So the first one, okay, is integers along with addition. Integers along with addition. So is this a group? Let's look at closure. Okay, we'll ask whether it's closed or not. Does adding two integers give me another integer? Is it true that if I add two integers, you give me another integer? What is the set of integers? Minus infinity, minus 1, 0, plus 1, plus 2, and so on till plus infinity. Well, it is true that if I do add or subtract, I will always be in this range. So integers are closed. Second thing is associativity. Associativity also. Usually when verifying whether something is a group or not, associativity usually does not create a problem. there are structures where associativity does not hold. Okay, but associativity usually holds. But if you see when we do addition, okay, when we do simple addition, okay, if I tell you to add three numbers, 1 plus 2 plus 3, obviously if it doesn't matter whether you do it in this direction or this direction, right? It doesn't matter whether you add 2 plus 3 first or 1 plus 2 first. So it does not matter. So it is associativity. Third is identity. Okay, what is identity? Does there exist an element such that when I multiply with it, I get the same element? Of course, there exists for integers, and for all integers, okay, multiplying with 1 will give me the same number. Whether I multiply with a 0 or minus 1 or whatever. Okay, 0 times 1 is 0, minus 32 times 1 is minus 32, and I'll always get the same thing. And finally, inverse. Inverse, is it true that there exists inverse for all integers? This is tricky. Why? Because take any integer, okay, let's say minus 27, or let's just say 27 times something gives me 1. This is the question, right? This is the inverse. What should sit here so that it will give me 1? Well, we know that the only possibility is that I put a 1 by 27 here and then I'll get equals 1. But the problem is 1 by 27 is not in the set of integers. So inverse does not exist, and therefore this is not a group. Okay, why? This 1 by 27 is a rational number or a real number. Okay, so 1 by 27 is not an integer, but we need the inverse also to be an integer. So that is creating a problem. It is not satisfying all the 4 properties, and hence therefore it is not a group. Okay, so yeah, can you tell me B whether natural numbers with addition, okay, is natural numbers along with addition a group or not? Not a group. Okay, Divya. Good. Let's see. Closure, associativity, identity, inverse. Well, closure, if you add natural numbers, is it true that they are close? It is true, right? If you add two natural numbers, you'll get the same. Associativity is also holding. I mean, it's like simple addition that we do. It always works. Identity is also holding, right? Because 1 is present, but it loses out in the inverse. Yeah, right, Divya, that's correct. So I mean, it's the similar arguments will follow, right? And this is not a group. So what about C? Can you tell me whether this is a group or not? Matrix. Okay. Before that, observe that if I replace this with even rational numbers, I'm done. Okay. If I give you rational numbers, I'm done. Why? Because now I have the inverse. So the rational numbers along with addition is a group. Okay. Yeah, anyway, let's move on. What about this? A matrix with multiplication. Okay. Matrix multiplication. M is the set of all matrices with real entries. Is this a group or not? So is matrix along with multiplication operation a group or not? Oh, okay, okay. I mean, so a set of all, say, n cross n matrix, okay, for some n. Sorry. Otherwise, it won't be closed itself, I think. I mean, not closed actually, because otherwise, some of the operations won't be defined itself because because of their dimensions. So anyway, the answer is that m along with multiplication is not a group. Okay. Why? Because well, closure holds because multiplying two matrices will give you a second matrix. Associative holds for matrices. Okay. There is a popular dynamic programming problem where we ask like how how we multiply, how we bracket matrix multiplications. Okay, but it does not matter. That's why it does not actually. This is possible because it does not matter in how in which way we actually bracket the matrices. So associativity holds. Doesn't matter in which order we multiply. Next thing is identity. This too holds. Why? Because we have something called the identity matrix, right? So identity holds. Anything multiplied with the identity matrix will give you the matrix itself, but inverse is a problem. May not always hold. And if I change the question to a set of all invertible matrices or set of all non-zero determinant matrices, then you may say that okay, inverse of a matrix exists, because we know that inverse of the matrix always does not exist, right? There is a test for that, okay, in linear algebra, and therefore the inverse may not always exist. So this is not a group. And finally, D, you will realize that D is a group. Okay, you'll realize that D is a group. It has all the properties of groups: closure, associativity, identity, and so on. Okay. So yeah, moving on. So I'm not doing D. Maybe you can try it as an exercise. Okay. So let's look at this particular question. Okay. The question says, which of the following statements hold for a group G and operation star? Okay, I'm given a group G and an operation star. The statement one is the following: let C equals A star B, where A, B, and G then A star C is in G. Statement 1. Statement 2. There can be multiple identity elements in G, but there can be only one unique inverse. Okay. Next. A star B, B star C, okay, and A star B first, then C is always true for all elements, and A star B star C equals C star B star A is always true for all elements. So can you think about these questions for a while and try to figure out what the answer is? Which of these statements are correct? Which of these options? Okay. I'll zoom it a little so it's properly visible. Okay. This is option B. Statement 1 and 3. I'll give some more time. Option, yeah, good to hear. Option B is the correct answer, right? Why? Well, the first one follows from closure. Okay. See, you're told that, C equals A star B and A B is in G. So we know that G is a group. So we know that it is closed, which means, multiplying elements within the group will give you another element in the group itself. So multiplying A and B give you C, but C should be in G because of closure property. Now what you are doing is C star A is also in G. Why? Because C also was a group element in G and A is obviously an element in G by assumption. Then this too is in G because again of closure. So statement 1 holds. Let's look at statement 2. There can be multiple identity elements in G, but there can only be one unique inverse. Well, the statement is very wrong. Why? Because there is exactly a unique identity element in G. It cannot be that there are multiple identity elements in G. And furthermore, there could be several inverses. In fact, per element there will be one inverse. Okay, so there can be multiple inverses. So statement 2 is trivially false. Okay. Third is A star B star C equals A star B star C is always true. Well, this is the associativity property of groups. Okay. Statement 3 is true by associative property. I mean, observe that all of these follow because G is a group. And finally, A star B star C equals C star B star A. Oh, okay. Now this is not very straightforward. Why this should be true? But one thing you can always say is this is a not necessarily a property of groups. So you don't need this to be true for it to be true. But this is what is popularly called follows from what is called commutative property. So if commutative property holds, then this is not this is true, but we know of examples of groups where commutativity does not hold. For example, if you take matrices, okay, you take invertible matrices which form groups, okay, which are groups, and try to check if this is true. You'll realize that okay, matrices, this is not true. We've done it using high school multiplication, right? In our school time, we used to say, okay, multiplying two matrices A and B is not always equal to multiplying them in the reverse manner, B times A. Okay. So statement 4 is false. Therefore, answer is B. Good. Okay. So yeah, let's look at question 7. The question says, which of the following tables represent groups on 4 elements? Okay. Okay. So what does this table represent? Okay, first I'll tell you. This represents operations. For example, let's look at this element. It means that if I multiply C with B, if I multiply C with B, I get D. Okay, this is what it means. If I multiply D with C, then I get B. Okay, final one. In this particular group G2, if I multiply C with B, then I get B. Okay, and these are what are called operation tables. Okay, question is now the operation tables are given to us. Now these are as good as giving you the group description, okay, description of the group. The question is, are these groups? Okay, so let's look for let's okay now let's try to solve this. Let's look at closure in all the three. These after operating, these are the elements that you get. You realize that all the elements are within A, B, C, D. So all elements in and these are the group elements, right? So if I had something like E here, then I'm going outside the group. So it should not, I'm going outside the set. So it should not be closed in that case, but we observe that, oh, okay, everyone after operation still lies within the ABCD region. So closure holds. Next we'll look for associativity. But as I've told you, I mean, usually associativity is actually assumed. Okay, so by assumption, in most cases, associativity is assumed that it's always holding, unless otherwise mentioned. Okay, and the third property is identity. Now, what was the definition of identity? There should exist an element, okay, E, such that for all A in G, for all the elements in G, if I multiply it with the identity element, I get the same element again. This is what it means. And so do I have such an element? Do I have such an element such that on multiplying I'm getting the same thing? For example, if I multiply with C with B, I should get C again. That is what I mean. Then B would be an identity element and so on. For example, if I multiply C with C, then I get C again. But again, D with C, I get a D again. So this seems to be an identity element. But If I multiply B with C, I don't get B. But I don't get B, I get D. So this is not, C was not this was not an identity element. But then I get this interesting feature that, oh, that means A on multiplying with something should give A, B on multiplying with that same thing should give B, C on multiplying should give C, and D should multiplying on with that identity E, okay, should give me D. Then this kind of a column A, B, C, D would represent the identity element. Do I have such kind of column? Yes, I have it here. I have such a column here. I have such a column here. In all the cases, it's A, A, A. So A is identity in G1, G2, G3. All three groups, all three sets, not groups yet because we have not checked whether they are groups. Now finally we check whether inverse exists. What is the definition of inverse? It is for all elements A, there should exist some A inverse such that on multiplying with A inverse, A with A inverse, I should get E. And in our case, what is E? E is A. Okay, I mean, there's a lot of overloaded notation, but I'll change the. For all elements B, there should exist a B inverse, either B star B inverse is equal to A, which is our identity. So look for such an inverse. So when we consider A, we have A. On multiplying with A, I get A. With B, on multiplying with what do I get A? D. With C, on multiplying with C, I get A, and with D, on multiplying with B, I get A. So, in other words, B is an inverse for D. So, all the elements have inverse. Again, I'll check. It is enough to check whether all the rows have A, the identity element or not. This row has the identity element, this row has the identity element, this and this. Here, if I check, this row has identity, this row has identity, these two rows do not have identity. Which means that if I take C and D, I can never hope to obtain any element from here in the same group, such that on multiplying I get the identity element. Identity element for us here is A. I don't have any hope of obtaining A again using multiplication. And therefore, G1, G2 have inverse but not G3. So G1 and G2 are groups, and therefore my answer is B. Okay. So I hope that is clear to everyone. Well, operation tables are useful in this way. Also, they can be represented in a very algorithmic way. Can represent groups in a very algorithmic way. Okay. Okay. Good. So look at this question. Okay. I want you to try your hand at it. The question says the following. Consider the set of words. Okay. Let me create some space. Consider the set words. Okay. W such that W is a word over English alphabets. Union epsilon. Okay. Where what does epsilon represent? Epsilon represents the empty word. Okay. Say in this imaginary world, okay, there is also something called the empty word. I can write something like an empty word. Okay. The concatenation operation, okay, the concatenation operation represented by dot, okay, single dot, attaches one word at the end of another. For example, sunny dot day equals sunny day. help.full equals helpful. Okay. The question is, does W dot form a group? W along with the set W along with concatenation operation. Okay. Does it form a group? That is my question. Also, is a word over English alphabet does not mean it's an English word. Okay. It could be, for example, something like A, X, B, J, K. This does not make sense to us, but this is in my set of words. Okay. Using the 26 letters of the English alphabet, any word that you create, okay, any random word that you create would be a valid member of the set. So the question is, along with this operation called concatenation, okay, what does concatenation do? It takes two words and uh, it joins one word at the end of another. Okay. So is this a group? Is this an example of a group? Okay, let me just charge. In the meantime, please try to solve this question. Charge my laptop. Okay. Yeah, let's try our hand at this problem. So we need to prove that W dot is a group, or disprove that it is a group. This is a question. Now let's look at closure. Okay, is it closed? Take any two words, W1, W2, in the set the words. Okay. If I attach W1, W2 at the end of W1, then it'll still be a word, right? It'll still belong to the set because it will still contain the same, consist of the same alphabets. For example, AXBJ dot ABJ will be equal to AXBJ ABJ. And this is ABJ. This is a word on 26 letters. So this should, by definition, be contained in words. Even if I take the empty language, okay, epsilon, and I attach epsilon times hello, I'll get nothing concatenated with hello, which is hello. This is still in the set of words. Okay, there's no dot here. hello, and this is still inward, so it is closed. Associative, well, you can say that it's satisfied, but we can even show that, we can also say that, hello, how are, or let's say uh, how you, okay, attaching these words. If you do this, if you attach how you first, then you get hello dot how you, which is equal to hello how you. Well, if you attach hello and how first, you get hello how dot you, and now you attach these two, you get hello how you. So you can see that associativity holds. You can take any two, any three words and try this. Okay, this holds. Associativity holds. Identity. Okay. So I'll give you some more time to think about it. Okay, what is the identity in this case? Do I have an identity in this case? A word attached with something will give you the same word. I'll give you some more time to think about it. Okay. What can I attach at the end of a word? Okay. What can I attach at the end of a word and get the same word again? That is the question. I mean, I actually showed it just now also. Maybe I'll show you this. Yeah. Well, the answer is the empty word epsilon. But this is the empty word. Okay. And oh, there's a lot of noise. Well busy, Ram. Can you mute? Yeah. Okay. Thank you. Yeah. So if you attach the empty word, okay, nothing at the end, then you get the word itself. Okay. Hello attached with the empty word will give you hello. So the identity exists for every word in the in our word in our set. Okay. So identity exists, and by definition, epsilon belongs to our, okay, there are too many epsilons here. Epsilon belongs to our words union epsilon. Oh, okay. Here should be union epsilon, because that is a set. Okay. Union epsilon, union epsilon. Final question is inverse. Can you take a word hello, multiply something to it, and then get an epsilon word? Can you concatenate? That sounds absurd, right? You take a word and you at the end you put another word. Anything you put here, any word put, okay, apple, ball, empty word, whatever, you cannot hope to obtain epsilon. You cannot hope to obtain the identity element. Therefore, it is not no inverse. Inverse does not exist. And therefore, the set of words, okay, with concatenation is popularly, there's a field called combinatorics of words, okay, which deals with these kind of operations on, English letters, and you can concatenate them, treating them as groups, okay, and not groups, they are called monoids, okay, structures without inverses. But yeah, inverse does not exist, so this is not a group. It is almost a group, as you can see it. And screen is not visible. For the others, is it visible? Divya, very Ram. Is the screen visible for you guys? Okay, Sharmila, what I'll do is I'll stop sharing my screen and I'll share again. Okay. Okay, I'm sharing again. Okay, Sharmila, is it visible now? Sharmila, is it visible now? I stopped the sharing and then I shared again. Can you hear me, Sharmila? You mean yes, Sharmila?
The screen is visible, sir, but the questions are not visible. That only I asked.
Oh, okay, okay. The question was not visible. Okay, sorry. Okay, okay. All right. I think should have shown the question once again, right? Okay, right. Okay, okay, okay. The question. Okay, I was sharing in the same uh, screen in the same screen. That's why maybe. So the question that I was addressing was this particular set. Okay, and words is a set of words or English alphabets union epsilon. Okay, and they could be any words. Okay, any random words which don't make sense, but they belong to the English alphabet. The letters belong to the English alphabet, and epsilon, where epsilon represents an empty word. It's like a word without any weight. Okay, represents an empty word. The concatenation operation, okay, represented by a dot, attaches one word at the end of the other. Okay, for example, sunny dot day equals sunny day, help dot full equals helpful, and so on. The question is, does W along with concatenation form a group? And then we checked whether it is closed because attaching one word with another. Okay, attaching one word with another will give you another word which consists of English letters. So it is closed. Is it associative? Where it does not matter in which order you concatenate. Okay, it does not matter in which order you concatenate. And finally, identity. Well, if you attach the empty word to a word, okay, you'll get the same thing again. So this empty word was necessary for our identity or property to be holding, and because epsilon works as the identity element. Finally, inverse. The question is, can you multiply something to a word, okay, such that you get the empty word? This is our identity, right? Well, that is not possible. It does not make sense how we can multiply something to a word. I mean, attach something to a word to destroy the entire word. So therefore, inverse does not exist, and therefore this is not a group because inverse property is not satisfied. Okay. Now we are at the end of the session. Okay. We'll look at subgroups. Okay. What is a subgroup? H is a subgroup of a group if H is a subset of G, okay, of a group G, okay, if H is a subset of G, and under the same operation it forms a group, which means it satisfies closure, associativity, identity, and inverse. All four properties that a group must have. Okay. Now, another important theorem in group theory regarding subgroups is, if H is a subgroup of G, then it is necessary that the size of the subgroup will divide its parent group. Okay, H is a subgroup of G. Then if you look at the size of H, then it will divide G. Okay. Now, here's a simple question. Okay. The question is, Z is a group of integers under addition. Okay, we know that Z is a group. We've seen in the previous question. Okay, that Z is a group of integers under addition. It satisfies closure, associativity, identity, inverse. Which of the following subsets of Z is not a subgroup of Z? Okay, so all of these are subsets of the subgroup. Now let's look at Z. Z is a subset of Z, and by the question itself is a group. By the question itself, we know that Z plus is a group. So A is fine. It is a group. Well, let's look at B. It is the group of all integers greater than equal to 0. Okay, the set of all integers greater than equal to 0. Or in other words, this is nothing but the set of natural numbers. Question is this a group? And the answer is that I mean let's verify the properties. Okay, if you add two natural numbers, you will still get a natural number, right? So it is closed. Associativity, yeah, it doesn't matter in which you add two natural numbers, 1 plus 2 plus 3, whether you do this first or this, doesn't matter. Identity, yeah, exists because 0 is the identity. Inverse, does it exist? That is the question. Can I add something to 2 to give me 0? Can I add something to 3 to give me 0? Always the identity element. The answer is that if I need to add something to 2 to get 0, I need to put minus 2, and here I need to put minus 3. But these two do not belong to natural numbers. Okay, these two do not belong to natural numbers, and therefore inverses that were supposed to be there are not there. So inverse does not exist. This is not a group. So I hope that was clear. Okay. So yeah, can you tell me about this one? So think about it. N consists of all the even numbers. The set consists of all the even numbers. Is this a group? So, I mean, closure. So we need to verify the four properties, right? Closure, associativity, identity, and inverse. So the set in C looks something like this, right? Set in C, n, so that n is an integer and n is even. Looks something like minus infinity, minus 2, minus 1, 0. Oh, sorry, there's no minus 2. Minus 4, minus 2, 0, 2, 4, 6, 8, and so on till infinity. This is what it looks like. So is it closed? Yes. Why? Because adding two even numbers gives an even number. Adding two even numbers gives an even number. This is a known fact, or you can even prove it saying that, oh, okay, 2k is the first even number plus 2l is the second even number is 2k plus l. Well, this is an integer, and this is even because it is multiplied by 2. It is closed. Associativity follows directly. It doesn't matter in which order you add, whether you add in which order you bracket things. Identity: an even number plus something is equal to itself. Well, the answer is if I add 0 to it, then I'll get itself, and 0 is even. So good. This is identity property is getting satisfied. Finally, inverse: an even number plus something gives me 0. Okay. For example, 2 plus something gives me 0. 4 plus something gives me 0. The answer is that if I put a minus 2 and a minus 4 here, then I get a 0. Right? And 8 plus minus 8 is equal to 0. Well, it turns out that, if this is even, this should necessarily be even. Because if I have 2k, I should necessarily add minus 2k. And this is even, always. So this belongs to my set of even numbers. Therefore, all the four properties are satisfied: closure, associativity, identity, inverse, and therefore it is a group. It is an example of. Okay. And the final one is an interesting one. I would leave this as an exercise. Okay. And here it's the set of integers which are divisible by 6, divisible by 9. Okay. A, this pipe, okay, this symbol A pipe B means that A divides B. Okay. What does it mean to divide something? It means it leaves the remainder 0. So are such kind of integers, okay, set of such kind of integers does they form a group? Check for the closure, associativity, identity, inverse. Okay, the four properties. If the four properties satisfy, then it is a group. Okay, I'll leave it as an exercise. Yeah, okay, the final question is a quick one. Okay, and look at it and try to think about how we may be able to solve this. Okay, G is a group on 78 elements. Okay, the largest possible proper subgroup. So what does proper mean? Okay, what does proper mean? Proper means that the subgroup that you get should not be equal to G. It's like a proper subset. Proper subset is a subset which is not equal to the superset, right? So what is the largest possible subgroup on G? And we saw a theorem called Lagrange theorem, okay, saying that if G is a group and H is subgroup of G, then size of H divides size of G. So now can you think about this problem? Can you use this Lagrange theorem Well, the answer is that the subgroups of G are actually just subsets of G, right? So, and we know by the Lagrange theorem that the size of the subset will actually divide the size of the original group. So if you have, so it means that if the group is 78, the subgroups can only have what kind of sizes? Could have 2 because 2 divides 78. Could have 1 because 1 divides 78. Is it divisible by 4? Well, it is probably not divisible by 4, but it is divisible by, say, so let's factorize it. Okay, 2 times 3 is 6, 9, and 3 times 13 is 39, and 13 times 1 is 30. So 13 divides it, 39 divides it, 3 divides it, and 78 divides it. Right? Now, well, you may say the largest subgroup is of size 78, but that is not the answer. Why? Because we are looking for proper subgroup. Looking for proper subgroups. Okay. Therefore, our answer is 39. Largest subgroup possible of G. Okay. So the answer is C. Okay. With that, we come to the end of the session and the end of all the problem session, weekly problem solving sessions also. And I hope the objectives were fine enough. Okay, and I hope you enjoyed these classes, and I hope that you learn to appreciate the field of discrete mathematics. And that is it. And good luck for the exams. Thank you.